So let's get started. And today I would like to talk to you about Planck constraints on the scale dependence of isotropic cosmic birefringence. This talk is mainly based on this paper here, which shares the same identical name. So as reference, you can search for this paper. So first of all, let me recall that when we observe the CMB signal, this signal appears to be polarized. And there are two different kinds of polarization, two different modes. The first one is divergenceless, the second one is curless. And inspired by the electromagnetic field, we can call these two modes as E modes and B modes. Because the standard model of particle physics does not foresee for any parity symmetry breaking in the gravitational and the electromagnetic sectors, we do not expect to find cross modes between E and B modes, meaning that we do not expect any EB power spectrum. But this is not the case because, for example, the Planck satellite data show a non-zero EB signal, as you can see here for one component separation method, which is Commander, but it is the same for the other three component separation methods, NILC, 7, and SMICA. And so the main goal is to understand if this signal is given by new physics beyond the standard model, which is breaking parity, and it is producing an EB signal, or it is just an undetected systematic effect. In order to make our project, our work, we have used the Planck PR3 data and simulations. From data, we extracted directly the power spectrum, while with the simulations, we have used the first 300 simulations of the signal, which have been produced using the Lambda CDM. And we added to these simulations some noise, some simulations of the noise. So we obtained two sets of simulations. The first 300, signal plus noise of the alpha emission 1, and the second set is signal plus noise alpha emission 2. Then we added masks in intensity and polarization. We crossed these simulations and we extracted the power spectra of the simulations. Here are the results of the power spectra that we obtained from data and from simulations for Commander and NILC. And as we can see, actually, there is something in the data which is not contained in the simulations, and it is not foreseen by the Lambda CDM. The same results for 7 and SMICA. So, if we would like to explain this signal through new physics beyond the standard model, we can use the Chern-Simons axion photon coupling. So there is an axion field which is coupling with the electromagnetic field through this Lagrangian term, which is called the Chern-Simons term. And this Lagrangian is breaking the parity symmetry, generating EB and TB correlations in the CMB signal. In this case, the axion field is acting like a birefringent fluid, and it is splitting the light dispersion relation, inducing a rotation of an angle beta of the photon polarization, as it is well explained by this picture by Minami. So in the case that we have a constant beta, constant angle, an isotropic cosmic birefringence angle, we have that the observed power spectra are different with respect to the theoretical power spectra on the CMB surface. And they are related to each other with this formula here. While, as you can see, if beta is equal to 0, the observed power spectra are equal to the theoretical power spectra on the CMB surface. So, in 2016, Planck parity violation paper have found this beta signal with a statistical error and also a systematical error which is compatible with the signal itself. This systematic error can be given, for example, from miscalibration angle alpha, given by instrumental systematic. And the problem is that alpha and beta have a certain degeneracy. There is a certain degeneracy between alpha and beta, because it has been demonstrated that alpha affects the CMB signal in the same way as beta does, meaning that the equations that I showed you in the last slide not only hold for beta, but also for alpha and for alpha plus beta. So there is this degeneracy. By the way, in 2020, Minami and Komatsu have proposed a method in order to break this degeneracy, and they have claimed, using the Planck 2018 data, that beta, there is a signal of beta of 0.35 plus an error which is accounting for statistics and systematics. There is also a more stringent constraint using the W map and Planck and other constraints given by other experiments. So, by the way, it seems that beta and the equations that I showed you in the last slide well fit the Planck data, as you can see here when I produced these curves using the equations for CMB, the observed CEB, with 4 different values of beta. So what we did, as we said, is to use Planck PR3 data in simulations. And we have performed not only an analysis on the whole harmonic range, but we have also performed an analysis bin by bin. So we divided the harmonic range into different bins with a certain width. And we have used this harmonic estimator called EBD estimator in order to estimate beta. This de-estimator has the property that if the estimated beta is equal to the real one, the estimator itself vanishes, meaning that beta can be found identifying the zeros of the estimator. First of all, we performed a chi-square analysis with our spectrum with this de-estimator. And we checked that actually data contain some signal, as we can see here, for the four component separation methods, which is not present in the simulations, which are generated with the lambda CDF. And this signal appears to be at 5 sigma with respect to the mean of the simulations. And it is important to say that it is unlikely, not impossible, but unlikely, that this signal is given by foreground residuals, because the 4 component separation methods deal with the foregrounds in different ways. So it is unlikely that this signal appears for all the 4 component separation method, and it is given by foreground residuals. Moreover, as we said, we have performed an analysis on the whole harmonic range and in different bins, obtaining let's say a power spectrum for beta. for beta signal on the whole harmonic range. As you can see here, commanders NILC, 7, and SMICA, where we obtained a constant beta with the analysis on the whole harmonic range, and we have obtained beta on the all beams that we have. So it is really important to understand if this signal is constant all over the sky, meaning that if this signal is or not scale invariant. If it is scale invariant, it is constant with respect to the harmonic scale or the bin. And we can actually use the equation that I showed you a few slides ago. So in order to understand if the signal is scale invariant, we performed an analysis using this power law, this model-dependent approach with this power law. And we have checked what happens to n, let's call it the spectral index. So thanks to the spectra that we have obtained with over the harmonic range, the spectra of beta, we have been able to perform this chi-square analysis, bin by bin. And from this chi-square, we obtained the likelihood. From the likelihood, we obtained these contour plots, where the important parameter is n. And we have checked actually that n appears to be compatible with 0 at less than 2 sigma. For commander and NILC, where commander is the worst scenario, where we have found 1.88 sigma, n is compatible with 0 at 1.88, and for 7 as SMICA. By the way, for all the 4 component separation methods, n appears to be consistent with 0 at less than 2 sigma. So this approach involved power law. So it means that there is a theoretical bias given by the parametric model. We have also made a non-parametric approach by reconstructing the data using a Bayesian analysis. In this case, we have used nodes or knots. We have set some nodes on the harmonic range, over the harmonic range, and the parameters are the positions of these nodes and the amplitudes of beta on these nodes. And we have reconstructed the data, the signal. So the reconstruction have been obtained with 4 different nodes, and we have compared what happens with respect to the analysis with n equal to 1, the analysis stating that beta is constant. We have used the uniform priors, both for beta and the L. Beta is spanning between minus 20 degrees and plus 20 degrees. And L is sampled uniformly over the whole harmonic range. The model that we used is called FlexNot, and the algorithm is pi-poly-cort. As you can see here, for all the 4 component separation methods, the Bayesian reconstruction using 4 different nodes and knots agrees with at less than 1 sigma on the whole harmonic range with the constant signal. So also with the non-parametric approach, we are saying that the Planck data agrees with a constant signal, a constant beta. Moreover, in the end, We have also made some forecasts for future CMB experiments, Lightbird, CMB-S4, and the SOLAT, despite CMB-S4 has been cancelled. But by the way, we started this work before the cancellation, so we have some results for CMB-S4 as well. In order to make some forecasts, to understand if future experiments can say something about scale invariance and can say something can constrain better or not the scale invariance of the signal, we have produced 1,000 simulations. The first 500 simulations were performed with the lambda CDM, meaning that in these 500 simulations, there is not beta. Beta is equal to 0. And we have generated other 500 simulations containing a CB signal with beta constant and equal to 0.3. These 500 simulations have been averaged and used as data. So we obtained that the signal appears to better constrain with future experiments. So in the end, our results are that using the Planck PR3 data, we have confirmed that there is an EB spectrum, and this signal is not compatible with 0, despite the origin of this effect is still under debate, meaning that we have performed our analysis regardless of the nature of the angle and regardless of the nature of what have produced this EB spectrum. We have performed 2 different analyses with a parametric approach involving a power law and a non-parametric approach. And in both cases, we have seen that the signal appears to be independent of the harmonic scale, meaning that appears to be constant all over the harmonic range, all over the sky. Moreover, we have made some forecasts with future experiments, and we have shown that future experiment can better constrain the amplitude, the signal, with error which are around 5 times lower, and also with the scale dependence, future CMB experiment can lower up to 7 times the error on the spectral index. So thank you very much for your attention.